Okay. So I'm on module 4. Now, this module has more definitions and vocabulary than any of the other modules. So I'm going to start this one off with the guided notes, which I highly recommend everybody doing for this section because there's a lot of words. But I'm going to start off by going over everything in the guided notes. And if I need extra things, which I will for a couple, I have them set off to the side so I can show that off. So I'll start with 4.1. 4.1 is about the types of data. So if you're checking on this particular section, if you are using the guided notes, okay, a parameter is a numerical measurement describing some characteristic of a population. There's the key word right there, of a population. Okay. P is with P. So a statistic is a numerical measurement describing a characteristic of a sample. Okay, so one's for the population, which is everybody in existence, and the other one is for the samples. Okay, so it's however much data we can gather. So we have two different types of data. Okay, the first one is called quantitative. Okay, quantitative data are quantities. So the weights of a supermodel, the ages of a respondent. This consists of numbers that represent counts or measurements. So weight, height, hair color, not hair color, how fast you can run a mile, that sort of thing. If it can be represented by a measurement, a numerical measurement, then it is quantitative. Okay, categorical is the other one. There is another name for categorical. It's qualitative. They are interchangeable, so I'm going to write it here, even though categorical is the most commonly used one. It's called categorical because these are categories. They consist of names or labels. Okay, so there should not be numbers, but there can be numbers. Gender is one version of categorical data. Shirt numbers on professional athletes. Okay, because it substitutes for their names, it is considered categorical. Okay, the numbers on a jersey do not represent any kind of measurable data. All right, and then when we're working with quantitative data specifically, okay, quantitative data can be further described by distinguishing between discrete and continuous types. Okay, those are two different types of quantitative data. So discrete data, this results when the data values are finite, okay, or countable. So the number of tosses of coin, that's 1, 2, 3, 4, 5, 6, 7. That's something you count. The number of people, okay, people are whole numbers, y'all. So the counts of people, the number of dogs that are in a animal shelter, like those sort of things are countable data. Okay, that's 1, 2, 3, 4, 5, or 6. You cannot have 4.78 of a dog. That makes no sense. So discrete data are countable. All right, and they're finite. There should usually not be a decimal. Okay, so blank. Oh, the other one is called continuous. So continuous data. This is data that results from infinitely many possible quantitative values. So this would be not countable, but this should be from an interval. Okay, so these are for intervals. Okay, these are for intervals. So an example is a distance from 0 to 12. This could be 1 or 2 or 3 or 4, but it also could be 1.578 or 2.333333, or any other numbers that are between 0 and 12. Even something like the square root of 11, that would work. The square root of 11 is 3 point something. Okay, so the level of measurement is the next thing that comes up. Okay, so this is classifying data. We can use 4 levels of measurement. Okay, each of them more in depth than the other. So the first one is called a nominal level of measurement. This is characterized by data that consists of names, labels, or categories only. Okay, So an example would be a survey response of yes, no, or undecided. Okay, those are just categories. I don't have any more in-depth information. I can't even order this information. Like I can't put it like least to greatest or anything like that. It's just, it is what it is, basically. Okay, so the next one after nominal is the ordinal. Okay, ordinal level of measurements. This is data that can be arranged in some order, but the difference when you subtract those data values from each other, it means nothing. Okay, it either means nothing or you cannot figure it out. So course grades are one thing. You cannot subtract a B from an A. That doesn't make any sense. Those are letters. You do not subtract them. Okay, and they're not even variables. They're just pure letters. The next one is an interval. Okay, interval levels of measurements. This involves data that can be arranged in order, and the differences between the data values can be found and are meaningful. However, there is no natural zero. There's no natural starting point. Okay, this is the key here. There's no natural zero starting point. There's nothing like this is the beginning of time sort of a moment. You don't know when time started. You just know where when right now is. Okay, and the last one is a ratio. Okay, ratio levels of measurements. This is when data can be arranged in order. The differences are meaningful. There is a natural starting point, and the differences and ratios are both meaningful. So this is usually when there's a difference between like times. Okay, so different times of running a mile or class times or manufacturing times, things like that, things that could be important. Okay, so the levels of measurement, categories only was the nominal. Categories with some order is the ordinal. Differences but no natural zero is the interval. And differences and a natural zero is the ratio. Okay, so the ratio is the most thorough. And the nominal is the least thorough. Okay, so one is much more in-depth than the other. All right, so the W's that provide us with context, who, what, when, where, why, and how, are my W's with context. I know how doesn't start with W, but it ends in W, so it counts. Okay, so the who of the data tells us the individual cases for which or whom we have collected data. So this is really important about who we collected data from. Okay, we will not always get it in a question, but it is extremely important if I want to make some sort of conclusion. So individuals who answer a survey are called respondents because they responded. People on whom we experiment are called subjects or participants if they're people. Call them participants if they're humans. We don't like to demean humans by calling them subjects, so we call them participants. Okay, we also have more animals, plants, and inanimate objects. These are called experimental units. Sometimes people just refer to data values as observations. And are not clear about the who. So observations are usually when I'm just trying to give you a question that I want you to solve, like the mean, where I just give you a list of data. These are observations that I have taken, but you may not know particularly where I observed them. Okay, that doesn't mean you can't do anything with the data. It just means you can't come to a very viable conclusion. So what and why, these are important. Okay, so variables are characteristics recorded about each individual. Okay, they're not just letters that represent an unidentified number. They are also characteristics that we record. The variable should have a name that identify what has been measured. Okay, to understand variables, you must think about what you want to know. That's really important. You must think about what you want to know. That is completely context-based, and you're going to have to read very carefully in these questions. Some variables have units that tell how each value has been measured and tell the scale of the measurement. This can be really important, especially if the scale changes from one sentence to the next. That usually means somebody's trying to trick you. Okay, so a categorical variable names categories and answers questions about how cases fall into those categories. A quantitative variable is a measured variable with units that answers questions about the quantity of what is being measured. Okay, so the questions we ask a variable, which is the why of our analysis, shape what we think about and how we treat the variable. This is extremely important because eventually all we're going to worry about are the conclusions that we come to. So if we do not understand the question that's being asked, we'll have no idea how to come to a conclusion. Okay, so this is the end of 4.1. So if this is all you needed was the 4.1 section, then you can go ahead and finish your pause the video or close out the video. If you're here for 4.2, we're just about to get started. Okay, so as an extension of the previous module section, subsection, however you want to call it, quantitative data and categorical data do not go away. So we're going to continue under this vein. So quantitative data, remember, consists of numbers representing counts or measurements. Categorical data consists of names or labels. Okay, so a bar graph is a graph of bars of equal width, that's extremely important, of equal width to show how the frequencies of categorical data. So the bars may or may not be separated by small gaps. Okay, usually in a bar graph, they are definitely separated. Okay, usually a bar graph, the bars are definitely separated. Bar graph shows the frequency, which is how often something happens. Okay, the frequency of categorical data so that it is easier to compare the different categories. Okay, if I know how often somebody has red hair, I can better judge if that's rare to have red hair or common. Okay, for the record, it's rare. All right, now there's a special type of bar graph, and it's only special because you arrange the bars. It's called a Pareto graph. Okay, a Pareto graph is a bar graph for categorical data. Of course, all bar graphs are for categorical data, but it's for categorical data with the added stipulations that the bars are arranged in descending order of height. Okay. So the bars decrease in height from left to right. So descending order of frequencies, descending order of height. It's really important. So you should start with whoever has the most, and then the second most, and then the third, and so on and so forth. Okay, so there's some features that come with these Pareto charts. And this is really important because these are the types of questions that they're going to ask you about the Pareto charts. Okay. It shows the relative distribution of categorical data so that it is easier to compare the different categories. What I mean by relative distribution is how one bar relates to the others. Okay, is it the highest? Is it the lowest? Is it in the middle? Does it match another bar? These are the things that I want to know about these bars. And it does show this pretty obviously because I'm supposed to arrange them. If you have two bars that are the same height, you can choose which one comes first. This also draws in attention to the more important categories, right? Because the more important ones would come first because they have the most frequencies. All right, so now we're on to the next type of graph, which is a pie graph. Okay, a pie graph is a very common graph that depicts categorical data as slices of a circle or slices of a pie, however you want to say that. Okay, in which the size of each slice is proportional to the frequency. Okay, so the biggest frequency will have the biggest slice of your pizza or circle or however you want to call it, pie. All right, so a pie chart will only show the distribution of the categorical data. It will not show anything else. Okay, pie charts are actually effectively useless in reality because you can't really draw any kind of conclusion from it. The best you can see is the difference between the different categories. All right, so graphs that deceive. Like, technically, this is the most important portion of the notes for 4.2. Okay, the first one is called the non-zero vertical axis. This means instead of starting at 0, so you can see how far away something is from the starting point, they'll start somewhere else. So it'll look like things start happening immediately instead of when they actually happen. Okay. Using a vertical scale that starts at some value greater than 0 will exaggerate the difference between the groups, especially if you start where the minimum bar will be. It'll look like that bar is nothing. Like there's nobody even in that category. Even if there was over 1 million people in that category, if you start at 1 million, then it's going to look like it's really small, even though it's not. Okay, so drawing of objects are called pictographs. And these are often misleading. Data that are one-dimensional in nature, such as budget amounts, are often depicted with two-dimensional objects like dollar bills, or three-dimensional objects like stacks of coins, homes, or barrels. By using pictographs, the artists can create false impressions by making something much larger than it is. Okay, this will just change how people view it. They'll look like the budget is huge, even if it's only $100, or it'll look minuscule when it's in the trillions. Okay, that's not okay, and we need to be very careful about that. So you need to pay really close attention to the scale of whatever you run into, because this is where people trick you. All right, and that is the end of 4.2. Okay, that is the end of 4.2, but I do have a representation of a pie chart. This is a pie graph. It was in color, but I don't have a color printer. And this one right here is a bar graph. It is not a Pareto graph for obvious reasons. My bars are not arranged in order. There are some things that you need to understand, that each section is labeled by a category and a percent. Okay, that's how a pie graph is. Each section of this pie is labeled by a category and a percent. Each bar is labeled with a word. That is very important. That's the biggest representation of a bar graph. And the frequencies are right here. But it's obvious to tell who has the highest. Blueberry is obviously the highest. Apple is the second highest. Grapes are the lowest. Okay, so these are things that you should be able to recognize from a bar graph or pie chart. All right, what am I on? All right, 4.3 is what's next. This is stem plots, time series graphs, and line graphs. Okay. All right, so stem plots are also called stem and leaf plots. These represent quantitative data only. There's only two forms for categorical data. It's the pie chart and the bar graph. For quantitative data, there's a lot more. So we start with the stem plots. All right, so stem plots will separate numbers into the stem, which is the leftmost digit, and the leaf, which is the rightmost digit. Okay, so you read this as this is the teens. So 40 is 40, 42 is 42. 50, 50, 52, 52, 52. So yes, you must repeat numbers if they repeat. Down here, once I got to 10, 10 and 2 make 102. So these two are 102 and 104. Okay, the leaves can only be one digit, and they must be in ascending order. So start with the lowest and go to the highest. Okay, repeats must be marked. This is all very important to do. All right, stem and leaf plots will show the shape of the distribution of the data. Okay, that's really important because we need things to be pretty symmetrical, and this will make it very obvious if it is or isn't. It will retain the original data values. I can see what the original data was. The sample data are organized or sorted, however you want to say this. They are arranged in order. That can be really useful, especially if I want a minimum or a maximum. Like, it will be very obvious to tell from this particular type of graph. Okay, and that's it for a stem and leaf plot. The next one is a time series graph. Okay, a graph of time series, which are quantitative data, right? This is measured based off of time, that have been collected at different points in time, such as monthly or yearly. We do this with our months and temperatures all the time, or rainfall. It's important to know when the most rainfall is because that's when you should, garden. Law enforcement fatalities. This has been I can't even say relatively. My dad was a former police officer. This has been utterly heartbreaking in the past number of years about how awful it is where people are literally hunted on the streets, whether they're law enforcement or not. That's not okay. But the law enforcement fatalities, it feels like it's much worse because they're plastering it all over the TV. But obviously you can see between 2000 and what looks like 2003, we had a massive spike in law enforcement fatalities. This would make me wonder. This would make me be like, what on earth happened in this year that made it so obvious? And I can actually answer that. This was when 9/11 happened, when the Twin Towers fell. It was 9/11, 2001. So this was the Twin Towers. A lot of officers died from that fall, from trying to help the survivors. So things like this are important because it also marks history. This is irrefutable that there's something that happened this year that made this huge spike. So features of a time series graph. This reveals information about trends over time. This can be important, especially with all these people yelling about the end of the world because of global warming or whatnot. Like, a time series graph would be very helpful for them. We have data about the climate going back over 100 years. That would be very useful. All right. So a line graph is the last one. The line graph can be used to visualize relationships between two quantities or show change over time. Okay. So this is the average daily temperature from for Omaha, Nebraska. Okay. So you can see the months: January, February, March, April, May, June, July, August, September, October, November, December. So these are the months. They just made them one letters. And then you can see the temperatures. You can see how the temperature will go up and then peak in July and then come back down to December, which it should. This is usually what happens in our daily lives. Okay. So I don't have anything extra to add other than for the stem and leaf. Okay, for stem and leaf, there should be a key that tells you how to read it. Okay, so like if I had a key that said, this was not 30, this was 3.0. Okay, this was not 30, this was 3.0. That means my data was 1 decimal data. Okay, so keep an eye out for that key because that will tell you how to read your stem and leaf plot for obvious reasons. Okay, so that's it for 4.3. That's it for 4.3. So I'm going to give you a moment to pause, leave, do whatever you need to do. So my next one is 4.4. 4.4. So 4.4 is goes with the 5-number summary or a box plot. The 5-number summary literally consists of 5 summary values. So the first one is the minimum. Okay, first one is the minimum. The second one is Q1. This is the quartile. This is the 25th percentile. The third one is the median. Okay, the median is also Q2. Don't forget that. Number 4 is going to be Q3. And the last piece of data is going to be about the maximum. Okay, so this is the 5-number summary. The minimum, Q1, Q2, Q3, and the maximum. All 5 of these are the last 5 numbers of the one variable stats on the calculator. Okay, so this is not something that you should have to be able to do by hand. You should just be able to read it. So we use this information to make a box plot. Okay, a box plot or a box and whisker diagram is a graph of a data set that consists of a line extending from the minimum value to the maximum value, and a box with lines that are drawn at the Q1, the median, and the Q3. Okay, so here's an example of a box and whisker plot. To make one of these, you have to start by finding the 5-number summary, because you can't make anything without a 5-number summary. Okay, this will construct a line segment extending from the minimum value all the way to your maximum value. And then we construct a box, a rectangle, starting at Q1, going all the way to Q3, and I mark where Q2 happens. Okay, I mark where Q2 takes place, or the median. Okay, now don't forget what Q1, Q2, and Q3 are. These are 25% of the data, right? So Q1 says that everything below it is 25%. From Q1 to Q2, that's another quarter gone, so that's another 25%. From Q2 to Q3, that's another 25%. And then from Q3 to the maximum is the last 25%. Okay, so that if they ask how much of the data, what percent of the data is from Q1 to Q3, okay, from Q1 to Q3 is these two 25%, which makes a total of 50%. 50% of the data is from Q1 to Q3. All right, don't let them trick you just because they're like, oh my God, how am I supposed to figure this out? They are quartiles. They make up a quarter of the data. So each quarter is identified based off of each marking made. Right, this is a nice way to summarize data. Very nice way to summarize data. This is it for 4.4, but I do have a second example of the box and whisker plot, just to point out something else. Now we know what a range is, right? The range is the maximum minus the minimum. But there is a second form of range, one that is less likely to be affected by outliers. It's called the IQR. Okay, IQR is the interquartile range. Okay, inter means between. Okay, so this is the range between the quartiles. So the IQR is Q3 minus Q1. Okay, it's Q3 minus Q1, and it resists outliers, which is important. Okay, it resists outliers, and it consists of about 50% of the data. So any of these pieces of information should be pretty obvious and easy to get if they've given you a box plot. All right, 4.4. There's 4.7. There's 7 sections, so I'm getting there. Now, a frequency distribution is conceivably the most challenging, so pay close attention if you're here for that particular purpose. Okay, so when working with a large data set, when I mean a large data set, this means something like more than 70. Okay, a large data set, more than 70 pieces of data. A frequency distribution, also known as a frequency table, is often helpful in organizing and summarizing the data. A frequency distribution helps us to find and understand the nature of the distribution of a data set. All right, so frequency distributions, they show how data are partitioned among several classes. Okay, classes is the most important word here because you don't use them in this particular context, but these classes are actually intervals. Okay, they're intervals by listing the categories along with the number of frequencies where the data values appear in each of them. So like if my classes were 0 to 4, 5 to 9, 10 to 14, okay, then my frequencies would be how many of my data values are from 0 to 4. How many of my data values are from 5 to 9? Those are the frequencies that go along with those classes. Okay, classes should not overlap. Classes should not overlap. There should be no number that can go in two different classes. All right, so these definitions are very important, so pay attention, write them down, try and get a better view of them. But I do have a physical copy of a frequency table that I'm going to point out each of these words. The first one, this is a lower class limit. Okay, this is the smallest numbers that can belong to each of the different classes. So in my three examples, my lower class limits are the 0, 5, and 10. Okay, if we have a lower class limit, we also have an upper class limit. This is the largest number that can appear in each of the different classes. So those are my 4, 9, and 14. Okay, the next one is a class boundary. A class boundary is the numbers used to separate the classes, but without the gaps created by class limits. So in this case, my class boundaries would be 4.5, right? Because it's directly between 4 and 5. 9.5, because it's directly between 9 and 10. And I don't have any other classes, so I don't need any other class boundaries. The midpoint, this is the value in the middle of the class. Each class midpoint can be found by adding the lower class limit to the upper class limit and then dividing by 2. The last one is called the class width. Okay, the class width is the difference between two consecutive lower class limits. So from 0 to 5, okay, if I subtract those, 5 minus 0, I get 5 as my class width. Okay. So there's some procedures for constructing these things. The first thing is you need to select a number of classes. Usually this is between 5 and 20. If you go less than 5 or more than 20, you will lose accuracy. Okay, so we want to calculate the class width next. We need to know how wide we need to make these classes. Round the results to get a convenient number. It's usually best to round up. Sometimes if you round down, your maximum no longer fits within your classes. So here's the formula for the class width. It's the maximum data value minus the minimum data value divided by the number of classes. All right, we choose the value for the lower class limit by the first lower class limit by using either the minimum or a convenient value below the minimum. Like if your minimum is 1, then you may use 0 instead. Or if your minimum is 11, you may use 10 instead, just because it's more convenient. I always recommend just using the minimum. Like just stick with the actual minimum. to use. Okay, so using the first lower class limit in the class width, we will list the other class limits. Okay, once we list the lower class limits in a vertical column, then we will list the upper class limits. Once we've done all of this, we will take each individual data value and put a tally mark in the appropriate class, add the tally marks to get the frequency. All right, so this is a lot of words. Let me show you what I mean. All right, so here is a frequency table right here. Okay, so what I would have done is I would have taken my minimum, which is 0. Okay, this particular question had a maximum of 24. I would take 24 minus 0, and I would divide by the number of classes. This one had 5 classes, right? 1, 2, 3, 4, 5. So this would be 24 divided by 5. 24 divided by 5 is a decimal, right? 24 over 5 is 4.8. All right, if I round 4.8, I'm going to get 5. So this is my class width. Okay, so when I choose my classes, I start at the minimum. And then in a vertical column, I will add my class width to get the next lower class limit. And I'll keep this up until I have my appropriate number of classes. Okay, so once I've completed this, then I need to make sure that my previous class ends one number below my next one. So if 5 is where this class ends, that means the first class ended at 4. If 10 is where this class starts, then the other class ended at 9. If 15 is where this class starts, then the previous class ended at 14. If 20 is where this one starts, this one ends at 19. And then if the class width is 5, then I must go 5 to round up my last class. So 20 plus 5 is 25. Okay, and then I take my tallies to I identify its total frequencies. Okay, so in this case, okay, I ended up with 4 for the first class, 3 for the second, 4 for the third, 2 for the second, and 2 for the last. So this makes a total of 25 data values. Okay, so this is a very crude, very quickly made frequency table. But this hopefully helped with all of these words. There's a lot of words to tell how to do these things. All right, so a relative frequency distribution. Okay, this is just a little bit different, but not by a lot. It just means instead of the frequency, instead of the counts of how much each thing happened, I wanted to deal with the proportion or percentage of each of these frequencies. So it's not particularly different, but different enough. So each frequency should be replaced by a fraction, which is a proportion, or a percentage, okay, one or the other. So the relative frequency for a class is represented, depending on which one you want. If you want the fraction, this is what you should use. You should take that frequency for a particular class and divide by the total frequencies. If you wanted the percentage for a class for its relative frequency, then you do the same thing, the frequency for a class divided by the sum of all the frequencies, but you multiply by 100 because that turns it into a percent. Okay, so relative frequencies, they should be a fraction or a percent, but nothing else. The sum of the percentages in a relative frequency distribution must be very close to 1 or 100%. Okay, so 1 if it's fractions, 100% if it's percents. You get a little bit of wiggle room because you get some rounding error. Okay, so it's as close to this as you can get. Okay. Now the cumulative frequency distribution, this is a little bit different. Cumulative, the word means the sums. So this is the frequency of for each class is the sum of the frequencies of that class and everything that came before it. Okay, everything that came before it. So if I use this particular example, okay, the cumulative frequencies, I'm running low on room, so I'm gonna say CF for cumulative frequencies. It's this frequency plus the sum of everything before it. My first one has nothing before it, so its cumulative frequency is still 4. The 3 has a 4 above it, so 3 plus 4 is 7. This 4 has a 3 and a 4 above it, so 4 plus 3 plus 4 is 11. This 2 has 4, 3, and 4 above it, so 2 plus 4 plus 3 plus 4 makes 13. This 2 has 2, 4, 3, and 4 above it. Okay, so this makes 15. All right, so the total of this particular section is 15. This is the total frequency. You'll find that the last section of a cumulative frequency is the total frequency. All right. All right, so calculate the mean from a frequency distribution. Now this is a little bit more challenging. So calculating the mean is first you must find the midpoints. Okay, you must find each frequency and each class midpoint. Then you must find the product of those. Okay, so this is the sum of the products of the midpoints in the frequencies. Okay, the class midpoints come from the classes. Okay, class midpoints come from the classes. An example is computing the mean for a frequency distribution is when working with data summarized in a frequency distribution, we make calculations possible by pretending that all the sample values in each class are equal to the midpoint. Okay, although we are pretending, we will get a good estimate of what the mean should be from this. Okay, the result is an estimate. Okay, it's an estimate because it is based on us assuming things about the midpoint. Okay, an estimate because it's based on us assuming things about the midpoint. All right, so just a few pieces of extra information. When we're finding descriptive statistics from a frequency distribution, we can find things like the range, which is the largest value minus the smallest value. We can find the mean, which is the sum of items divided by the number of items. This has the symbol of X bar. The median, which is the middle number in a sorted list of numbers. Or the mode, which is whichever has the highest frequency. That is a mode. And I am done with 4.6. Or 4.5. I'm sorry, I'm on 4.6. 2 more sections. Okay. So while frequency distribution is a very useful tool for summarizing data and investigating the distribution of that data, an even better tool is a histogram. Okay, a histogram, which is a graph that is easier to interpret than a table of numbers, let's be honest. So a histogram, this is a graph which consists of bars of equal width drawn adjacent to each other, unless there are gaps in the graph. Like if there's a class that had a frequency of 0, there will be a gap there. So the horizontal scale represent the classes. Okay, represent the classes of the data, and the vertical scale represents the frequencies. So the heights of the bar correspond to the frequency values. So whichever has the highest bar has the highest frequency. All right, it is important to use a histogram for certain things. This visually displays the shape of the distribution of the data. Okay, so you should be able to better make conclusions about its shape, its center, its spread, that sort of thing. It shows the location of the center of the data. This should be something I should be able to see. It also shows the spread. And it should identify any outliers. All right, if I got something pretty far away in a gap, then it should be obviously an outlier. Okay, there's not just a plain histogram, there's a second version of the histogram. It's called a relative frequency histogram. Remember, a relative frequency is the percent. It's the percent of the frequency rather than the frequency count itself. But a relative frequency histogram has the same shape and horizontal scale as a histogram. So the vertical scale is marked with relative frequencies instead of actual frequencies, but as you can see, they should still look identical. So I should still be able to obviously find the center, obviously find the spread, that sort of thing. So as you can tell, these are percents, so these are relative frequencies. Okay, this side has counts, 0, 1, 2, 3, 4, 5, so on and so forth. So therefore, it is the frequencies themselves. So these are what histograms look like. The bars are touching, obviously. There's no gaps here. They are all the same width. If they are not the same width, then somebody is trying to trick you. They're trying to bring focus onto things that don't deserve focus. All right, so there are 4 different shapes, possible shapes. There is a bell-shaped distribution. This is called a normal distribution. This is what we want. This is what we want. This is the one we want. There's a uniform distribution where everything is about the same. Everything appears about the same in frequencies. There is skewed to the right and skewed to the left. You know if it's skewed to the right or skewed to the left. Skewed to the right will have a tail on the right. That's why it's skewed to the right. Okay, if it's skewed to the left, then it won't have a tail on the left. Okay, that's how you can tell. Because this histogram is roughly bell-shaped, this one right here, because this histogram is roughly bell-shaped, we say that the data have n approximately normal. Okay, this is approximately normal distribution. Okay, it's not perfectly bell-shaped, but it is very good bell-shaped. So it is approximately normal. Okay, obviously, because there is a bell drawn on it. And it lines up with the data pretty nicely. All right, so a distribution of data is skewed if it is not symmetric. If the left does not match the right and extends more to one side than to the other. So data skewed to the right, this is positively skewed because it's skewed towards the more positive numbers, have a longer right tail. Data skewed to the left, which is negatively skewed because more negative numbers are on the left, have a longer left tail. So this is how you can identify these different shapes. Okay, it should be very obvious from a histogram which one is which. And if it is not obvious, then give it your best try. All right, with histograms, we want to note the shape, center, and spread of each of the distributions. This is what we want, shape, center, and spread. So box plots bring those back. Box plots, 2Ps, offer an ideal balance for information and simplicity. It hides the details that can be too eye-catching or distracting, while displaying the overall summary of information. We often plot them side by side for groups or categories we wish to compare. So here we go. We can obviously see how much higher April is than the rest, right? We can see that some of these have outliers. If it has an individual dot off to the side, this is an outlier. Okay, you can have multiple outliers. The month of June had 3 outliers. Okay, you can have multiple outliers. If there are any clear outliers and you are reporting the mean and the standard deviation, report them with the outliers present and with the outliers removed. Okay, if you show both when they're there and when they're not there, you can tell what those outliers did to that distribution. Did I pull it more to the right? Did I pull it more to the left? Did I make this unusually large or unusually small? That's important information. Note that the median and the IQR are not likely to be affected by outliers. So this is why the box plots are so useful, because the box plots show the median and the IQRs, right? This is where the box plots are so useful. Okay, box plots are so useful because they show medians and IQRs, and they are not really affected by outliers. All right, last little bit. For some data sets, we are interested in how the data behave over time. In these cases, we construct a time plot of those data. Okay, we construct time plots of the data. They kind of look scatterbrained, but the bottom axis should be some form of time. Okay, the bottom axis should be some form of time. What can go wrong when comparing data? The first thing is you want to avoid inconsistent scales. If the first histogram goes by 5s, then the second histogram better also go by 5s. Okay, so this should be either within the data or when comparing two data displays. It should not be 5, 10, 12, 14. It should be 5, 10, 15, 20. Okay, the scale cannot change in the middle. Make sure to label clearly so the reader knows what you're talking about. Okay, if they don't know what the data displayed is, then the data display is effectively useless. Beware of outliers. Okay, they highly affect means and standard deviations. So if that's what you're looking for, then they're going to seriously screw you up. So be aware of them. Be careful when comparing groups that have different spreads. Okay, different spreads. If I have 2 histograms side by side and one is much wider than the other, for example, this one's spread is 60, right? Actually, it's approximately 50. This one goes from 50 to almost 100 to about 95. So while these bottom scales are different, their spreads are about the same. But because the scales are different, how was I supposed to know that? These look like these should go together, even though this one is much further to the right. Okay, this one is much further to the right according to this, even though it is left skewed. So be very careful about what can go wrong. Keep an eye out for these things. This is how people trick you into making decisions you shouldn't make. So be very aware of these things. All right, I know this was a lot of words, but this is why the guided notes for this particular section are so ridiculously important. So please come in and get them from me. I don't have anything extra or special to make for you, so I'm going to end it here. If you have any questions, y'all know how to get in contact with me. I will see you later.